All right, so today we'll be talking about building a custom query engine with Quill. I'm Martin Snyder. I'm the CTO of Wingspan Technology. Wingspan Technology makes document management applications for regulated industries. And this is not something we do yet, but it's something that we are definitely taking a look at doing in the future. And this story actually started almost 3 years ago when I did a local presentation on building a CRUD data store in Scala. It was fully immutable. And the concept was to have all the properties of a relational transactional system, but not be based on SQL in any way. And there was use cases for this that aren't really important for today's talk. But it had constraints, and most importantly, it had a query optimizer. So when you did a query, it could optimize the query execution based on the existence of constraint data. And we'll be looking at a couple simple scenarios. But just to kind of follow the examples, we have to all be on the same page here. So we have a very simple data structure, a person, they have an ID and a first and last name. And then right here in this second part, we're building the actual data store. And the data stores can be heterogeneous. They can store records of multiple types. And in our case, we're only going to be populating it with people. And you can see that important fourth line where we have a unique constraint on the ID field of people. And then we're going to create a bunch of worker bees, 2.5 million in this case, just to get enough data in there that you can tell the difference between a index hit and an index miss. And then we're going to also just put Mr. Allen and Ms. Baker into there, just because we want people that don't all have the same last name for one of the scenarios. So that's the data that we're dealing with. And we have three different ways that we can access this data using the data store. So the first one is kind of the obvious choice. So this is an in-memory pure Scala library. It makes sense to use Scala predicates to request data. So in the first case, we have given some connection to this data store. We can apply a filter against people, and we get everyone with the last name of Allen, which happens to only be Abe, right? And then in the second scenario, we're going to apply a filter against people where the ID is 1, and here we get the first worker bee. Okay, and these both take in this run, they actually took the exact same amount of time. They take similar amounts of time, and the reason they do is that they both degrade into the equivalent of a database full table scan. They have to apply that predicate to every single record in the data store, and then return just the ones that match. And it's not impossible, but it's very difficult at runtime to analyze that predicate in a way that you could apply it to the unique constraint and do any better. There's another downside of this, which is, and Spark is a special case, but generally speaking, you can't serialize Scala predicates. So if I wanted to have a RESTful API that front-ended this, and this was my only way of accessing it, then I would have to invent a new query language to expose through the API, because I can't put a Scala predicate on a URL. So there's limitations here in a couple things, but the one nice thing is that, as you can see very clearly, the query mechanism is 100% type safe, right? So that's good. We would, at compile time, solve a lot of problems that we might face. So we have a second technique, and this was what the previous presentation was all about, was having this alternative query language. So if you're using a database, it would be SQL, but in this case, because we're in memory, we just have a bunch of case classes which represent the different conditions. And it's not exhaustive because it was an example project, but the primary one we use is this equals condition, where you want to return all people where the family name is Allen. It's the exact same condition we were just looking at in the predicate. And we can see here, we get the exact same result in that first example. It takes a little longer. It takes longer because the implementation is using reflection to actually apply the condition. It's not really important. The key thing is that it's doing a full table scan, because there is no constraint on that last name. But then when we do the second test and we look for the person with ID number 1, you can see that executes almost instantaneously. And mechanically in the data store, what happens is when it goes through the constraints when it's resolving the condition, and it says, oh, for each constraint, can you resolve this condition? And the unique constraint's like, yeah, I sure can. And it gives you the one record, and you're done. Like, you don't actually hit the query engine. It hits the constraint resolves this. And if you had some composite condition with an and of several terms, you can imagine how it would apply that just to the one condition, and then kind of do the right thing as it builds out over time. So this is great. right? We get that very fast execution on the second case. But the problem is we have a complete loss of type safety. If we specify the wrong attribute name in that first part of the equals condition, we won't know until we execute. If we specify, a value that's the wrong data type, maybe the thing will just always be a miss. Maybe you'll get a runtime error. It kind of depends on the implementation under the covers. But the big thing is you won't know, and you'll find out, at some time potentially in the future in the form of a page or an angry phone call. So now we have this third technique, and this is what I built for today's talk. So this uses a library called Quill, which has been around for a year or two. I wasn't familiar with it until recently, so I don't know how widespread the knowledge of Quill is. But we can see here that syntactically, we have something very similar to Scala predicates. There's a little extra stuff going on. We're not connection based anymore. We're using this context. But you can see like we're designating the type in almost the same way. If I just flip slides for a second, retrieve records is designated to the type of record we're retrieving. And here we're doing some sort of query which is similarly designated. And then we have this filter which is using a Scala predicate. And if we go back 2 slides, we'll see the Scala predicate applied is exactly the same. And the first one takes the performance is comparable with the conditions. And the reason for that is that at compile time, what you're looking at here gets compiled into the actual condition. And so it's going to use reflection to execute. But the bottom one is the key, right? The bottom one, we have a Scala predicate. We are type safe. It compiles, though, to a condition which can be interpreted and optimized and hit the index. So if we kind of summarize this is the timings off of those 4 different cases. And the green ones are type safe and the red ones are not type safe. And we have one green 0, and gee, that's exactly what we want. Like that's the holy grail of all of this, is we don't have to make this trade-off between type safety and being able to actually analyze the query. So what this talk is really about is how we achieve this, because Quill out of the box is very a very well constructed and capable library, but it supports JDBC and it supports Cassandra. And so if you have a JDBC data source, you can just use Quill out of the box. You can stop now. You just go to their page and follow the examples, and you'll be perfectly happy. This talk is about extending Quill to use things that Quill doesn't support. So one really good example of something that people might want to consider, and the makers of Quill might want to consider, is NoSQL databases, things like Solr. I mean, Cassandra, it does, but Cassandra has made greater attempts to look like SQL. I mean, they have their own query language, famously named SQL with a C. So it's easier to make those two marry than it would be to extend to something else. So the other case is if you have anything like this, anything anywhere in your code where you're constructing queries in a non-type safe manner, then the techniques I'm showing you here could help you. Basically have type safety and then compile to literally the exact same thing you're using today, and you don't have to change the rest of your code. This only comes into the compiler side. So what we end up doing is we have to build a Quill context. A Quill context is kind of the ultimate marriage of all of the concepts that are within Quill. Well, again, we're going to take a deep dive into all of these things. But so we make a context, and in this case, the context is aware of data stores, and then we separately give it a list of all the record types in the data store. We'll get to why that is later. But if you had a JDBC context, it has to know how to connect to the JDBC data source, for instance. And then we import a bunch of implicits from that context, because this is how the compiler is going to know what to do. This quote, this is magic. That is the thing that is doing everything that everyone's asking the questions of how does this work. Quote is how it works, and quote is a Scala macro. It's not like a Scala macro, it is exactly a Scala macro. And what we do when we extend Quill is we write regular Scala code, which will be ultimately invoked by that macro at compile time. And so you put quote around the thing that you want. So we have a query segment, and then we have the filter that's applied. And You can support things of arbitrary complexity subject to your ability to translate them to what you're going to do. Now, I was very fortunate here is that I applied this to a research project which had a very simple query language. So it didn't take me that long. But if you had a comprehensive query language, that's a fair amount of work. So it's not something that you get for free. There is a lot of work involved. And then the context itself is able to run that compiled query. And I've expanded it so you can see the types a little more clearly. The one thing to note is that you cannot apply a static type to this compiled query. Well, so that's not exactly true. You can, and you can get it to work. But if you do, it's going to take away a lot of the compile time functionality, and Quill will give up and degrade to runtime compilation. So there is a lot of this. There is the types are there, but you don't want to be explicit when you're dealing with the quoted structure. That's from their docs also. It's not that's not something that I found out on my own, although I tried to put a type on this slide just to do it, and it ends up being so ugly you're better off just closing your eyes for that part. So we have two parts. Okay, we have a compile time part where we're going to take that thing inside the quote, and we're going to compile that into something of our own creation. And then we're going to have a runtime part that will take that thing of our own creation and execute it. And from this point forward, the code examples we're going to look at are greatly simplified. I'm leaving off methods that aren't germane to the exact things that I'm taking you through. And I've substituted some pseudocode in some spots versus showing you the whole methods. All the code is available in the project. I'll have a link at the end, and the slides will be available later as well. So if you do go navigate through the code, you'll find very similar stuff, but it won't be exactly what's on the slide. The biggest thing the condition does is it has this translate method, which translates between the abstract syntax tree of the Scala compiler, and it produces a statement. And a statement is a Quill concept, but ultimately, by virtue of some of their design decisions and their API, a statement is going to be something that is ultimately resolvable to a string. There are a couple different flavors. We'll see all of them by the end of this talk. Now, for people that know the Scala compiler well and have done macros before, you'll immediately scratch your head about what this AST class is, because that's not going to be a Scala AST. It's a Quill AST. I talked to some of the maintainers about this, and what they said was that they developed their own parallel set of AST classes because Quill can't handle everything. There's a subset of Scala syntax that can be quoted, which makes sense when you think about it, because there's a lot of things that you can do in Scala that you're not going to be doing in a query scenario. And they wanted people implementing things like this to be able to have exhaustive match statements, and they didn't want to force people to match stuff, against the Scala AST that was not a feasible thing. So it helps. It's pretty powerful. The more you know about the Scala compiler, the more it will help you when you're doing stuff like this. But it also helps you to kind of narrow the scope a little bit and have an easier job of doing it. So we have this very simple filter we were looking at. We just want to filter where the ID equals this constant value. And so in this one case, I've taken some extreme liberties in my my broad capabilities to have a pattern match against that exact scenario. So it turns out I just want to extract the attribute name when we're equal to some constant value. And then I can build my own equals condition. And it seems like we're almost done, right? This is the exact same equals condition from my second technique. And it looks pretty good, but we're at compile time, and we've converted that predicate. So we got the type safety of the compiler against the predicate. It's happy that ID is a field of person, and it's happy that the constant I provided was of the correct type to be compared to the ID. So it's done all that validation. I got the compile time type safety, and now I'm going to substitute into the bytecode the equivalent of this equals condition. There's one minor issue we see at the end here, which is the Quill API wants a string. In this case, it's taking a string token, but that class isn't important yet. It wants a string, and it wants a string because they support SQL and they support Cassandra, and those both represent their queries as strings. So for their world as it exists right now, that's okay. I asked them about that, and they said that it's not set in stone, so they could maybe loosen that. And so this is a little bit of a minus for me in this case, where I actually have at compile time exactly what I want, but because of the way the interfaces are set up, I have to stringify it. So the conditions in my primary data store, they're not JSON serializable, but I wrote a little module here to serialize them. There's not enough conditions to really worry about. So we convert it to JSON, and again, that's a arbitrary move here just to satisfy the Quill framework. And so then we get to that context.run, the step 2. This is going to happen at runtime, and this is what the class looks like, where we get the data store and we get the record classes, and all of the contexts look the same way, where they extend some base context, and there's a couple different ones. There's this notion of an idiom, and the idiom is, what sort of query are you constructing? There's a notion of naming conventions, and in our case, because we're in memory, like our case class is exactly what our query representation is. So we can use a literal, we don't have to do any magic, but you can camel case things, you can add underscores, you can write your own naming convention, because a lot of times your case class may not match up exactly with what's on the other side of the query. So there's a whole world there that we're not going to be talking about today, because I didn't need it to extend my personal project. Now there's encoders and there's decoders, and we're going to skip them for now. And we can skip them for now because this first scenario was so simple. We're doing a comparison against a single attribute using a constant value. There's really nothing to do. The thing that's going to come out of JSON is going to be natively executable. That one equals condition is going to shoot right through. And so we can get this query out of the JSON. And then here's that exact same data store execution that we would have had in scenario 2. So at runtime, we're doing the exact thing. So we have the compile time produces conditions as JSON, and then at runtime, I deserialize and I execute, and everything's exactly the same. So if you were doing this on your own project, this one line at the bottom here, that's where you pick up where you left off. That's where you enter the world you already created, and you shouldn't need any changes there. Like everything that you've done to support your own custom query constructs, that's just going to work. This is all just compiler magic and then some glue to get back into the world where you started from. And then normally we were doing this with Scala generics, where we were specifying the type and the generic position, and just because this is now at runtime, we have to specify the generic type in an implicit that we was previously unseen. Not important to what we're talking about, but does answer questions that people might have had about that one missing piece of syntax. So that's that. So now there is another category of thought, which is very important, which we're going to see here. So now we have a more complicated scenario where I've written a method which is going to take an input parameter and is going to apply this to the query. Okay, so ID, it can't build a full equals condition at compile time, because if you just think about how the compile works, it's going to have a slot left for the actual runtime value of ID. And the quote can handle this, but you have to tell the quote, you give it a little helper to tell it that you need to do special work for this thing. And that's what the lift is, if you see in the bottom right of the code sample here. The lift is basically telling quote, hey, we're going to have to slot ID and jam this in. So this is where things get significantly harder, just as a as a general note for people. So we rush through things to get to this point, because from here and all the challenges afterwards, there's a lot. The AST is more complicated, the wiring is more complicated, but ultimately it's all still supportable. So we end up having to update our idiom, and I've left out the other stuff. The other stuff is still there. We can imagine. I think that people are starting to see that this match off the AST is not only going to be much bigger than we're indicating on the slides, but it's also potentially recursive. If you have any sort of nested conditions, like an inversion, like a not condition, or any sort of conjunction, like an and or an or, you're going to have a recursive pattern match that you would apply against these things. And at compile time, we need to construct an equals condition because we know we're going to need it, but we don't know what the value is right now that we're going to compare it against. And so in this case, I've just put 3 question marks to tag for later. You can actually keep track of the number of replacements that you have, what they call the lifts. You can keep track of all of those, and you can use index-specific placeholders. This comes into play later because what we're trying to do, and this isn't strictly necessary for us. This is we're trying to be as compliant with what Quill is already doing. And so there might be better ways to achieve this, but this works pretty well for us because an equals condition takes an any or any ref, like we can stick almost anything in there, and we can change the type of an equals condition. So we're not really going to worry about any type safety concerns with that. We just want to put some placeholder in. And then we get to the more complicated statement. And this is really, really important, is the quote doesn't know anything about the lift unless we propagate that information. So before I said, oh, well, I've converted this. I made my condition in memory, and now I'm going to convert it to JSON, and I made this string token, and that satisfied the type constraints of a statement. So I made this string token, and it had my JSON, and we're good. We're out. But if you just do that, then Quill will never give you the value back. Quill will assume that you somehow absorbed it or ignored it or something. We have to put a scalar lift token into our return statement, or we won't get the good stuff. That took me a little bit to figure. I think it's obvious in the end, but my hope was that it would still kind of thread it through, because I don't need this. Like, I know what's going to happen because so much of my construct is already in memory. Like, I could have put any sort of sentinel value into this equals condition such that I could have scanned for it later and done a replacement if they'd given me the runtime value. But I don't get the runtime value unless my statement includes a lift token. So a statement, this high-level statement construct, you can build hierarchies with it. It has a list of statements, which can include other statements. So you can imagine, given a list of lists of lists, you can build whatever hierarchy you need. And it's ultimately going to stringify it. So this presented another challenge, because my scalar lift token is going to be stringified, and I'm trying to build JSON payloads. So if I just JSONify my condition, then I'll get like some extra junk on the end of that, which you can ignore, you can do different things. But what I really wanted to move towards was I wanted to move towards a compliant JSON object which looked the right way. We're about to see what that looks like. And now the context gets a little more complicated as well, in that the first thing is right here in the retrieve records, we now prepare the condition. So we skipped over it before, but when we are told to execute, we're given the query that was produced at compile time, and then we're given this prepare, which can take a row and produce a new row. So if you were in SQL, what that would look like is it would be, okay, well, given this SQL prepared statement, you can prepare it for execution, and you'll get a new SQL prepared statement back. And so we would just call, you would say, okay, well, value 1 equals question mark, and value 2 equals question mark, and then we're going to set index 1 to be this value and set index. You can see how the post processing would work for SQL. So we're going to do something similar, and that's where during this prepare function that they give you, that's where Quill will give you that value at runtime. So if you don't have any lifts in the statement that you return from your idiom, then you're not going to get any values. The prepare is going to be the identity function, and it's going to skip over. That took me a little bit to figure out. And so now we get to other stuff I skipped over. So we see that a data store context extends a context, and it has encoders and it has decoders. And what an encoder is an encoder, quite literally, is something that takes a value at runtime and applies it to your query. Okay, so again, you have a JDBC prepared statement. It just calls, set int with the given index. This will feed you all of the lifted values in the order that it encountered them in your sequence. So if I was using string.format, then my placeholder token would be something like, %1 $s, $2 $s, and then you could just do a string.format with all of these things, and probably the right thing would happen. In my case, I'm just looking for the triple question mark. The actual code handles the indexes properly, but since our base scenario is straightforward enough, we're just going to stick with that. So if it matches that, then if it matches the equals condition with the placeholder, then we produce a new equals condition that has the runtime value. and we can ignore index in this case. But if there are scenarios where you might have to do enough tracking where that index becomes valuable, and then anything else it just does unmodified. So again, if we were dealing with conjunctions and larger hierarchies of conditions, you could imagine how this would pretty easily just recurse to find the right thing to replace it, and produce the right answer. So just going back for a second, encoders are done on the in. So quote produces a compiled version of your query. The encoders apply runtime values at runtime to the query prior to execution. Then you execute, and then the extractors will take what you produce out of your execution and will convert it back into the case class that Quill was expecting. Right? We said it was a quote of a query of person. So it has to return a sequence of people. So you have to get it back into that structure. Now in our case, our native format is the original case class. So we don't do anything with the extractors in here. We don't do anything with decoders in this entire example. But honestly, I think that's the easiest part. Going from the answer just at runtime, going from something like a result set to a single case class, most people can figure that. And Quill will help to make that happen more efficiently. But in my case, I just skipped it entirely because there was nothing for me to do. And here's what my JSON query format looks like. So one of the things that's interesting is that, when I have the condition library and you say, this is a query for type person, it's the actual class person. Quill will only give you the short class name, the get simple name off of the Java lang class object. And I have no way of directly getting back from that to the full class name to do the type safety that I want to do at my execution. So that was why when I was building my context, I gave it a list of all the classes that were in the data store, so I could iterate over them and match it back up and find the right thing. So we have to capture that information so we know what type to apply the condition to. And then the condition stuff is pretty simple. We talked about JSON serialization of conditions, and so that just slots right there. And then those liftings, remember how I said that it's the nature of Quill to want to include additional tokens that correspond with the lifts? And if you don't include them in that statement, you're not going to get the right behaviors. So I actually built a JSON format that would allow them, even though I technically ignore them. I could imagine maybe it would be valuable for diagnostics or something. You might imagine some use of it. And so in the actual code project, there's a little more complicated thing where in what we were looking at, I just returned these very simple statements of just the condition and just the liftings. But there's like a prelude and a postlude that puts more of the JSON structure around all of that so that we get the right thing coming across the wire. And again, the fact that it has to go to a string at all is just a happenstance. And just by way of comparison, I put the equivalent SQL query on the below there, so you can see what it would look like if you were doing if you're doing the exact same filter against a JDBC data source, you would see something like that, subject to what you did with the namings of the thing. So Quill has some very important features in this area. I've mentioned a couple of them. I just wanted to be very clear that these are three things that I didn't do for this example because I didn't need to do them. They didn't apply because everything I'm doing is already in memory, and the case class that we're pumping through Quill is actually the native data object we're getting back. The coolest thing Quill does, without a doubt, is probing. So we talked about how Quill will at compile time, do the type safety and will compile it to my condition object. When you're using the JDBC features of Quill and you turn on quoting, it can go one step further. So it will compile at compile time and produce a SQL statement. It can syntax check that SQL statement against the database. The context has connection information in it at compile time in the probing scenario. And it can type check that. So if my case class had a attribute, which even with the naming stuff doesn't correlate with a column, I will get a compile time failure. That's amazing, right? You really have to see and think. But you can imagine there's a performance hit on compile time, but you can compile with or without probing. But it's exactly the sort of thing you might want to do on a continuous integration server. You catch some stuff that would otherwise, you can imagine very easily how with all of this type safety, you can still have, but what about this? This closes a lot of those gaps. It's not perfect, but it's incredibly potent. We mentioned the result transformation. I didn't need to do it. It's very similar to the encodings. And it just depends on what your structure is. Like when you build a context, you get to say what your runtime query representation is. So if you say it's a JDBC prepared statement, then then your encoders are dealing with that. And if you say your result row is a JDBC result set, then your result transformations are going to work with that. So it's pretty straightforward. The key thing is just kind of getting into the game. Once you can get even basic functionality going, then it's very easy to build out what you need. And the naming algorithms is an important part, right? Because you want your case classes to match your programming API, not necessarily your schema API. And you can imagine a world, if you get into something complicated enough, where you write a custom naming algorithm, which is simply just a map, right? You're not algorithmically, going from ID to ID. Your ID becomes, object ID or something, just completely arbitrary. You can do whatever you need to do to make this work. It's obviously more work. So one of the questions which people have been waiting to ask is, how does this compare to Slick? Because there's properties of this which are very, very similar to Scala Slick. And so the biggest change is that both of them have compile time type safety, and they look very similar. Quill has compile time query generation versus runtime query generation. And that doesn't really, I think, change people's worlds that much. There's minor benefits of doing that. But when you factor in the probing, it's a significant capability to have the compile time query generation with type checking the query against the data source is a significant advantage versus Slick. And the nature there is really demonstrated of the two techniques. It's not the sort of thing that Slick could bolt on, nor should it. I mean, it's not a better or worse. It's different, and that's the advantage. Quill makes a big deal about how you can just use these case classes as is. You don't have to go and build a lot of extra structure. So for people that haven't used Slick, for that person object, I would have had to make a Slick table query, which represented all the rows in Slick constructs, and then did some other things. So that's it's definitely it's more work to use Slick, but Slick has much broader capabilities. Like Slick can actually take those definitions and build the schema in the database for you, which Quill can't do. You can define indexes and foreign keys and stuff in Slick, and those will be created, and that's like completely, it's the same thing. It's not what Quill is intended to do, nor should it, and it's not something that can be bolted onto Quill. So they definitely have pros and cons. Another nice thing, which you don't really pick up unless you use them a lot, is that the predicate we were using with Quill is just a regular Scala predicate. The predicates that you use in Slick, they are actual, they're like operator overrides. And like the big one that everyone always gets on is there's a triple equals you have to use in Slick because you can't override double equals. And that really draws attention to the fact of some of the differences that are going on. I think that's more of a personality fit thing, and not so much of a it doesn't really make a huge difference. But if it's something that bothers you about Slick, and it's complicated. If you step into some of those operators in Slick, you're going to learn a lot, or possibly nothing. But just depends on how long you're in there. And Quill, of course, Quill doesn't do nearly as many things as Slick does. So choosing, there's a lot more written on this, so you can find some blog posts and forum articles and stuff. Generally speaking, if the use cases overlap, my guess is you'd probably be better off with Slick. More people use it. Don't swim upstream. But there's a lot of use cases, and the one I'm looking at today is one of them. There's a lot of use cases that Quill can do and Slick can't. Right? Like Slick is 100% JDBC. You can't use Slick with Cassandra. You can't use Slick. I can't use Slick to build custom queries for my in-memory data store. Or maybe I could. Well, I can't. Maybe someone could. But it's not an intended use case. I don't think it's necessarily worth the effort. So I don't think there's really the potential for a Quill versus Slick war. I think it really they're different enough. If you're starting from scratch, it's worth learning both. Whichever one you choose, knowing the other will teach you more about the one that you choose. So where do you really want to use Quill? If you want to do what I did, you're looking for any place you can replace unsafe, non-type safe query construction in your source code. anywhere that exists, you can do what I did, and you can get type-safe query construction, and you'll be better off. It comes at a cost, but you can do that. So that's one thing to look for. The probe, if you have any problems, even a little related with that, where it's like, oh well, someone changed this field I didn't know, and now I get this weird query. No, that's easy to fix. But usually when you say, oh, that's easy to fix, you're talking about a production defect, right? And I mean, this, if you're in like an agile, very fast to production organization, you're talking about finding that probably 2 to 4 weeks after the problem was introduced, right? Versus finding it the same day. It's really, really powerful. If it's possible to take advantage of that, I think it's worth giving Quill strong consideration for that feature alone. And then, if you're in one of those overlapping scenarios and you're really concerned about code size, I think that if they both handle the scenario, I think your solution with Quill will be less code. Again, I think that's a factual statement. How much of a benefit that is, I think that depends on personality and raw numbers and stuff. When you go down this path, there are a few things to be careful of. The first is that you have a lot of code dependencies, especially when you're working on your Quill extensions and you're testing them. You have a lot of code dependencies that won't be detected by SBT or IDEA or Maven, because every time you change something in your idiom, for instance, that has a compile time impact on everything that uses quote, and no one detects that. Right. So what you'll end up doing is, okay, well, I changed my idiom, and now I have to remember to clean before I compile. Otherwise, I'm not going to get all the good stuff. Okay. So that's something you get used to it very quickly. But it's just worth noting, because that's always very frustrating when you're working with something and you don't see. It's like, oh, my changes are having no impact. Like that, people lose confidence in the technology very quickly when you get that, and you fail to get traction, and that makes it harder for you to be successful and therefore harder to adopt the technology. So that's very, very important. Again, that only applies down my path. If you're just using Quill for what it does out of the box, you're not going to have any of those issues. But if you're doing anything that happens inside the quote, then you're going to run into that. Debugging macros is hard. There's great articles written about this. Ultimately, what you have to do if you really want to debug a macro is you have to run the Scala compiler through the debugger, which, look, the odds are if you're writing a macro, that's not going to scare you. but if you're writing a macro in the context of a library like Quill, and so you're not really a macro developer, then that might scare you. And my advice here, there's a great answer, is don't debug macros. What you can do is at the end of any quote statement, you can add .dynamic, and that will tell Quill not to compile it at compile time, but rather compile it at runtime. And then you can debug your stuff using the normal debugger. Right? You just want to make sure you turn that off. And there's no way to turn it on globally. You have to do it on a quote by quote basis. And that might be good too, because you're going to hit up a lot of breakpoints if you start, quoting a bunch of stuff. So, that's an important capability to know. There's other ways you can trick it into doing a quote at runtime, and they're almost all things you want to avoid. So that's, you always want to be doing this stuff at compile time. Like there's things that, like if you give it something that violates its rules in such a way, it'll basically say, look, I lack the capability to compile this. You want to stay away from stuff like that, although it's tempting to sometimes trigger that to be able to debug it easier. So use .dynamic, and that all goes away. There's a high knowledge barrier to coming down the path that I went down. There's not a lot of documentation on doing extensions to Quill like this. The best documentation you are at the tail end of at this moment. But also, you're going to have to know about how the Scala compiler works. Quill makes no effort to really shield you from that, and nor should it. I mean, it's the abstract syntax D is what it is. You got to be able to understand what's being produced by the compiler if you're going to be successful in translating it to something else. So again, I lucked out there because my query language was incredibly limited, and I didn't even implement the whole thing. So, but in a real scenario, that translate in the idiom is not at all obvious what you should be doing there. And the best examples are within Quill itself. I mean, they have a lot. They have like all the JDBC stuff has a hierarchy of idioms, so you can get like a MySQL specific one. There's something called a mirror idiom, which you can either use out of the box or extend, and that helps to give you the AST at runtime, so you can dump it and debug it. And there's other things that happen with things being emitted during the compilation process and stuff. So if you start using Quill a lot, there are a lot of tools. They recognize that this is not an easy place to operate in, and they have some tools to make that easier. So that's all I've prepared for you today. There's a link here to the repository Quill and my personal blog. The best source of information is to start with getquill.io. The maintainers are very responsive if you ask questions on the chat. That's how I got some of my questions answered in producing this material. And that's it. So thank you very much for listening. I have time for some questions.